was it or not?
I'm
Just
not
got
sure.
here.
He goes in.
Yeah. I've never experienced it. Where'd you go?
Yeah.
We started at 5 past last time, but I know you have Angus, you somewhere here, right?
At 1/4 past, yes. I've got. I can do it on my tea time.
Okay. Then maybe let's wait 2 more minutes.
Man, the legend.
Tea time is right.
Are you speaking for one of these? Yeah, I go with them.
Let's maybe because it's not my tea time. I received.
Oh, that's cool.
How are you? Northwestern time, and it's always fun. It's fast. Just Andrews. He's towards the wait 2 more. Of course.
I wonder who that is.
Wonder if there's any connection.
One more minute.
First or second? Because I'm in the sense I'm not sharing my iPhone. Yeah. I know. Zap. Sheer foot.
Is it since I passed? We should probably get started. So thanks to all of you for being here. Those of you who are on Zoom, thank you also for being here. It's very exciting for me to get to hear what the grad students here are working on. I'm hoping I will understand some words of it. And our first speaker is Angus, who is going to talk about materials for fusion energy and the Kev Lab.
Thank you. So, I'm the first speaker, so I get to introduce all of the fusion stuff to you this Fusion Energy Week. First things first, I'm just going to go over what fusion is, what are our requirements, and then a little bit about what we do in the lab. So, first of all, this is a slice of the ITER tokamak, which is like the next big nuclear fusion device in the south of France. It's about 6 meters in major radius, which is the distance from the center of the plasma over to the center of the device. So it's kind of like this donut-shaped device, and you're squishing your plasma inside the donut. So this is a cross-section of that donut. You're slicing into it and seeing our plasma, which is our main way of producing fusion energy. The plasma itself is made up of hydrogen, so deuterium and tritium, which are heavy hydrogen. We smash them together and hope that they stick together and get our energy out. If you want to do this, you've got to have all this stuff around it to make it not just fly out, right? You've got lots of positively charged stuff in there, and you're trying to squish it and make them go together, but they really don't want to go together because light charges recover. So around that, we've got a lot of plasma-facing components, which experience a lot of heat. Plasma core itself is like ultra-high temperatures, 100 million Celsius. And the plasma-facing components themselves don't get that hot because nothing can get that hot. But they are at thousands of Celsius. And then around those plasma-facing components, you've got to have something to hold it up and keep the vacuum that's required for this at vacuum level. So we've got a vacuum vessel, and then also we've got some magnets around the outside that sort of squish everything together and make our plasma behave the way we want it to. And that's a very sort of rushed overview, but the point I'm trying to make here is that everything in there is made up of a lot of materials. So we've got superconductors in the magnets, which themselves are like these complex layered structures, these superconducting tapes. The vacuum vessel itself is made up of many things, so they're all welded together. The plasma-facing components has a lot of cooling and a lot of candidate materials that could be there, all of which have to be evaluated. And then that's not even talking about cooling or breeding of fuel, which in itself is a huge challenge we're working on here. There's a lot of stuff, and they all have to survive what is created by the plasma itself. When we do fusion, we get a lot of energy, hooray, and we also get a lot of radiation, which is both our best friend and worst enemy. Radiation is how we get energy out, but it also does a lot of damage to our materials as well. So that's kind of me singing for my supper. Why do we actually care about radiation material science and what we do in our lab? We need to know how our device is going to behave. So what do they do? What do these things do in the material? For example, a neutron can come in, hit our nice, in this case, crystalline material. All of our hard work, forging, melting, heat treating, we spent so much effort making this nice omelette, and then the neutron comes in and just turns it into scrambled egg. So it comes in, it can knock atoms around, it can transmute atoms where the neutron is absorbed, it turns into something else, which has a lot of knock-on effects, but there's a lot of extra stuff that can happen inside a material that can degrade it. Secondly, in the plasma-facing components, we've also got this idea of erosion, so something extremely hot and extremely we use plasma elsewhere in industry to erode materials and redeposit them elsewhere. Like that's how we do all of our semiconductor manufacturing. You just fire plasma at something and let it sputter away. So we don't want that to happen, but it wants to happen very much. So what we do is, what can happen is the plasma itself, which is typically hydrogen or helium. Helium is the waste from the fusion process. Helium can go into the material, and at high temperatures it can form these bubbles. In this case in tungsten, which is one of the candidate materials for the plasma-facing components. And it can form these like bubbles which can then grow and then rupture, and they make this fuzzy stuff on the surface, which is not great because you don't want little bits to break off and start whizzing around inside your plasma. That will waste a lot of energy. So what does this actually do? Radiation damage stuff, this is just some examples of kind of like how bad could it be? You can get. Why do we like metals in structural materials? Because they can flex a little bit and not break. But in radioactive environments, your metals can go from being very ductile in this case. So here this is a plot of energy to breakage and against temperature. So for a normal material, we can absorb a lot of energy at room temperature and not break. Whereas if you irradiate this has just been taken into a fission reactor for some amount of time. If you radiate these, you can start to have this, what's called ductile fracture, brittle fracture, rather than ductile fracture. So when something starts to break, you want it to like bend a little bit, you don't want it to just snap. So big degradation there. You can also get swelling, which is a bit more intuitive. Your materials can grow as little gaps inside them coalesce. And if you've made things to a certain tolerance, which they definitely will be in these fusion devices, then this can just completely ruin that. You also get a loss of thermal properties as, like I was showing in the previous slide, your crystalline structure gets all messed up, and your electrons, which generally carry all of your heat and electricity in some cases, it can't flow as well. So you can get a loss of thermal properties. In this case, we've got neutron dose on the x-axis here and thermal conductivity on the y-axis, so you can see it drops by a factor of 4 plus over some exposure. So you want to know what's going to happen here. How do we actually figure that out? So in our lab, we have a look at various material properties. I'll just go kind of through the various beamlines in the lab, which is an accelerator lab. So at the back here, we've got the accelerator itself. This is the thing that makes our ions, and we can hit our materials with our ions and just see what happens. On the left, we have a corrosion beamline. I was mentioning coolant and fuel breeding earlier. Those things, if you have something that's effectively, if you imagine what corrosion is, it's your material comes in, it interacts with the surface, and then it goes away and carries some material away with it, perhaps. If you have lots of radiation kind of like moving things around, it's effectively like stirring your cup of tea with a spoonful of sugar in it. It just helps that process along, or you can grasp that it helps things along. So we need to assess how that's happening. One of the backbones of the modern tokamak design is the superconductor. We don't really know how radiation affects that very well. And if that's like your most expensive critical showstopper, you kind of want to know how that's going to go. So we have a beamline that looks at how radiation affects those materials. And we also have this plasma device that can do simultaneous radiation and plasma exposure at the same time for plasma-facing components to evaluate them. And on the right, we also have a laser technique that we can use to evaluate things as they're being damaged at the same time. I'll go over that in a minute. Okay, so the corrosion stuff, we have this little cell. You've got liquid metal on one side of this foil, which is this target looking device. So there's a little foil of metal. We've got liquid metal in this case on one side of the foil and high vacuum on the other. We're shooting irradiation through, seeing what happens in a certain irradiated region versus unirradiated. And I was I completely lost my train of thought. Sorry. Oh, yes. I was saying earlier that you can effectively speed up this process of corrosion with radiation. But in this case, it's counterintuitive, because what we saw was, in fact, the corrosion was slowed down by radiation. So this is a paper that was published off of that. And in the center, you can see where we have radiation, there's actually less corrosion that happens. So we're still finding these like counterintuitive effects that you can observe when you try and interact this radiation stuff and the corrosion stuff at the same time. I have a few more slides that go over kind of like the other beamlines, but I think in the interest of time, I will simply skip to the end and ask for questions before I head off. So we've got some laser stuff. If you have questions on any of those other beamlines, I'll be happy to take them now. Thank you very much.
Any questions in here or in the Zoom room? We've got about a minute at most.
Is the reduction in corrosion with irradiation, is there a mechanism that's understood at this point, or is it still sort of a mystery?
They proposed that, in the paper, they proposed that a lot of the corrosion happens along grain boundaries. So your corrosive material, your material is made up of many grains, and between those grains, it's kind of like the material is not so well held, because it's kind of just like this chaotic structure of atoms. And so the corrosion tends to happen more efficiently there. And so the region around that grain boundary is depleted in this case, chromium. It was leaching chromium out of the material. And the idea was that what's happening with the process of diffusion in the grains is slow to the grain boundary compared to the process of diffusion within the grain boundary into the liquid metal. The idea was that they proposed was with this kind of like churning effect from radiation, that enhanced the diffusion within the grains to the grain boundaries. So it kind of pumped it full of the things that it lacked, in this case, the chromium, and kind of allowed it to survive a lot longer. Whereas before, that was just getting depleted and then eroded.
Any more questions? Mostly concerned about getting you out of here in time.
Sure.
If not, let's thank Angus again. I was about to call you Sean. And Sean is next up. I'm not going crazy. All right.
I can plug in.
Yes. So only if you have the display on that screen. Some people will see it. Do have a little bit of extra time because one person canceled, so we should be fine. Okay. We'll have to leave. He just had to leave.
All right.
So now we have Sean Mackey, who's going to be talking about studying burning plasmas with fancy science.
Hi, I'm Sean. So I'll be telling you a little bit about studying burning plasmas with neutron emission spectrometry. So first of all, just a little bit about, let me just get rid of some of the stuff on my screen so you can see it. So fusion reactions produce energetic nuclear particles. Deuterium and tritium are isotopes of hydrogen with extra neutrons, and it's the most reactive mix of fusion fuel we have. When deuterium and tritium react together, it emits an alpha particle and a neutron. The energy that's stored in the nuclear bonds within the deuterium and tritium is released in the form of kinetic energy in these products. And since it's a two-body kinematic reaction, the amount of energy that goes to the neutron and the alpha particle is a discrete quantity. Every time you get 14 MeV of energy to the neutron and 3.5 MeV of energy to the alpha particle. Now in a magnetic fusion situation, you have a strong magnetic field which confine the alpha particle because it has a net positive charge. But the neutron is uncharged and so it escapes, carrying with it about 80% of the energy liberated from the nuclear reaction. So the goal of any sort of fusion reactor and research into fusion is to get more power out than we put into the plasma. And so the key metric that we use to quantify this is called the gain factor. We call it Q. It's defined to be equal to the ratio of the power out minus the power in, so the net power produced, divided by the power that you put into it. And so if you assume that you're in a steady state thermal equilibrium, this reduces to the fusion power divided by the heating power. If Q is greater than 1, that means more energy was produced than you consumed to actually heat up and produce the plasma. And the point of this plot on the right is just to show that, through the years, we've made a lot of progress towards actually achieving this goal. On this plot in the top right-hand corner, that's Q greater than 1. And you can see all these dots and shapes represent previous fusion experiments and the sort of trend towards high gain regimes. And so now after, 6 decades of research on the topic, we're basically right on the brink of energy break-even. At the National Ignition Facility, if you saw Maria's talk on Monday, they've actually already achieved this. And so we know that it's possible to get more energy out than in from these types of reactors. We just need to make it sort of commercially relevant or economically relevant. And so, okay, if our goal is to make Q greater than 1, how do we actually know if we've achieved that goal? We need to somehow measure the energy or the power gain of the reactor. And so the denominator of that expression, the input power, that's pretty easy to measure. You could just call up the electrical company and say, hey, how much power did I use to heat up my plasma? And they'll say, oh, you used a megawatt or whatever. The output power is a little more tricky. And so the most reliable method that we have to actually measure how much fusion is going on, the power liberated from fusion, is to count neutrons. Since each deuterium-tritium fusion reaction makes 1 neutron, the fusion power will be proportional to the neutron emission rate. And so if you can count your neutrons, you can infer what the fusion power was. My research is all about developing advanced neutron detection methods for the SPARC tokamak. You may be asking, well, what the heck is SPARC? If you missed Alex's lovely talk on Monday. SPARC is a demonstration device designed to generate net magnetic fusion energy. It's being built by a PSFC spin-out company called Commonwealth Fusion Systems. They're building this reactor out in Devens. On the right, I have a picture of the SPARC facility, and then in the pink box is the interior of the tokamak hall. You can see a picture of what SPARC will look like printed on the back wall of that room. And then on the left wall, you can see the neutron camera slit, which is that all vertical slit and a number of other diagnostic access holes through the primary shield wall. So Spark is designed using high temperature superconductors, which, like Angus mentioned, is like sort of the key technological breakthrough that's enabling fusion to really sort of take the next step. These magnets are more powerful than previous generations of magnets, and they confine the plasma a lot more strongly. So you're able to achieve higher temperatures and densities without, sort of having to put in a lot more power to maintain those densities and temperatures. And one of the key parts of Spark's mission of proving that net energy is possible with magnetic fusion is having a really robust set of neutron diagnostics and neutron measurement techniques. In addition to just telling you about how much fusion is going on, neutrons also carry a lot of information about the plasma. So if you can make a nicely resolved measurement of the neutron energy spectrum, you can also diagnose plasma parameters such as the fuel ion temperature, the bulk plasma density, the ratio of fuel ions, so deuterium to tritium, if it's not 50-50, and also sort of more subtle effects like the heating power coupling, or more sort of subtle things beyond that as well. And on the right here, I just have a plot showing how the thermonuclear neutron spectrum changes as a function of fuel temperature. So in blue, you can see relatively low temperature plasma. 4 keV is the units that we use. It's sort of low amplitude and skinny, and as you increase the temperature, the amplitude goes up, there's more fusion going on, but also the distribution gets wider because the thermal broadening of the neutron emissions increases with temperature. And that broadening actually increases as the square root of temperature. So you can measure your neutron spectrum and measure how broad it is. You have a measure of the ion temperature, which is really useful for assessing how well your plasma is actually heating up and things like that. Okay, this thing goes to 11. Spark is designed to reach Q of 11. So while Q greater than 1 is a big milestone, to be economically viable, you really need Q to be much larger than 1. Because you need to take into account all the inefficiencies of the plant. And so if we really are reaching Q of 11, that would be really great because it would demonstrate that, okay, this reactor concept, it's actually scalable to economically viable levels. But from a scientific perspective, once we hit Q of 5, the majority of the plasma's heating is actually coming from the fusion reactions itself. And so this state where most of the heating is coming from the fusion itself is called the burning plasma state. And it's a new regime of plasma physics that hasn't been studied experimentally. And so that's what I'm really excited to work on. And so you can probe a lot of the interesting novel physics of the burning plasma regime using neutron spectrometry. And so there's a couple of ways to see this. Like, first of all, the neutron spectrum is in a sense the twin of the alpha particle birth spectrum. Because they're both being born from the same reactions, the spectrum of neutrons is intimately related to the spectrum of alphas before they have a chance to slow down in the plasma. So that's an important input to modeling what's going on in the plasma. Also, nuclear scattering becomes really important at these high gain regimes, and that manifests itself in the neutron spectrum as a high energy tail. So if you can measure that high energy neutron spectrum, you know something about how the fusion products are actually slowing down and heating the plasma. So that's a useful input as well. And so I've spent a lot of my time here at MIT developing what's called a magnetic proton recoil spectrometer. And so that's what I'm showing on the bottom right here is a schematic of that diagnostic. It's basically a giant proton beamline, and you generate the protons by having neutrons scatter them out of a plastic foil. They go through a big magnet system and get sorted and focused based on their energy, and you detect them in a detector array. And so you have this position resolved measurement of the protons, which is in turn related to the energy spectrum of the neutrons. So in summary, neutron measurements are critical to validating fusion reactor performance. The neutron energy spectrum encodes a lot of useful diagnostic information about the plasma, including the ion temperature, the fuel composition, and information about the heating. And the burning plasma regime is an unexplored scientific territory, and neutron spectrometry gives us a way to empirically map the terrain of this new regime. And then this is just a picture of me and the rest of the neutron diagnostics team for Spark standing in front of the neutron camera slit, which is where we're going to put a lot of our diagnostics. Happy to take any questions.
We have time for a question or two if we have any.
So I was wondering about so you mentioned about the efficiency as comparing the amount of power you put in with the power which is stored inside. But I'm wondering about the physics of how this power is going to be converted in a useful way into, let's say, electricity and so on.
Right.
In a few words.
So in a real fusion reactor, you're not just looking at these neutrons as a diagnostic tool, but since they're carrying out 80% of the energy from the nuclear reactions, if you could thermalize those neutrons, you could drive a thermal cycle. And so the leading idea is that you would have some sort of neutron moderator to catch all these energetic neutrons, slow them down and heat up that moderator, and then you can boil water with it and turn a turbine.
Thank you.
Any other questions that we're squeezing in? If not, let's give Sean a hand again. And Abby. When Abby gets up here, I will tell you what she's talking about. I should have asked for titles before. You're a USB-C, right? Just get rid of this. All right, so Abby's going to be talking to us about exploring runaway electron impacts in spark, which we just learned about.
All right. Hi, my name is Abby. I'm a grad student here, and I'm going to be talking, just like Lauren just said, I'm going to be talking about exploring runaway electron impacts in spark, and I'll define what those are in just a minute. So, like everyone else has been talking about, I'm also still talking about tokamaks. And one way that I like to think about tokamaks is that tokamaks are trying to contain jello with rubber bands. So what we're doing here is we're containing a plasma with magnetic fields. And so you've got magnetic fields that wind around the tokamak in both the toroidal direction and the poloidal direction. And these contain your plasma. And these the reason that we're all talking about tokamaks is because tokamaks have been the best at confining plasmas so far. They have better confinement than any other fusion device that we've been able to build so far. However, they are quite unstable, just like if you had jello in the middle of a bunch of rubber bands. And so if something happens, if it goes slightly off, you can have sudden losses of your plasma. So you can have your plasma suddenly be lost from the device, hit the wall, and it can lose a lot of its energy very fast. So this is known as disruption, and these are bad for business. If you're trying to make fusion energy and make money off of that, it's very bad if you lose your plasma, because you lose your fusion and you're no longer producing energy. And one other thing that can happen during disruptions is you can get beams of relativistic electrons. So in a tokamak, when it's operating in its nice steady state, it contains megaamps of plasma current, which is a lot of current. And so when your plasma gets unstable, you can transfer this current into these relativistic electrons. And these are known as runaway electrons because they're in essence running away. And so you've got this beam of electrons spinning around and around and around in your tokamak, and then it has to go somewhere. And if you're hearing this and you're thinking, oh, a beam of very high energy electrons, that sounds like sort of familiar to me, you would be correct because this is the same thing as lightning. So you can think of a beam of runaway electrons as sort of a beam of lightning in your tokamak that's going around and around and around until it has to go somewhere. So when this beam of relativistic electrons goes somewhere, you can get damage. So what I've got here is I've got a video from the Alcator CMOD tokamak, which was a tokamak that was here on campus at MIT. And you can see in this video, it's pretty boring. The plasma is transparent, so nothing is really happening. And then it starts to get a little crazy, and then boom, you've got a beam of runaway electrons, which hits the wall and causes sparks. So it's melting the wall because it went unstable and it hit the wall, and then you got some melting, some sparks. Very exciting, but also very bad. And this is not unique to Alcator CMOD. We've seen this across several experiments across the world. So we've seen wall melting, metal vaporization, and even a magnet quench. And if you quench your magnets, your tokamak stops working. So we've seen this across several experiments. And here I've got just sort of a fun collage of damage that's been caused by runaway electrons. So the CMOD damage up in the top right corner, and then also JET, which is a tokamak over in the UK. Textor and West are two other examples of tokamaks that have had runaway electron beams hit something and cause some melting. So this can be bad for tokamaks that we've seen in the past. But the question is, what does this look like for power plant-like devices? So when we go to the future and we're trying to actually make power and then make money from our tokamaks, how does this scale to that? And the answer, and before I talk about what the answer to that is, I want to just talk about Spark really quick. Sean already did a great job of introducing it. So Spark will be the first tokamak to achieve Q greater than 1. So more fusion power than the power you're putting into your tokamak. But what this means for Spark in comparison to other tokamaks that have previously been run is that Spark will have a higher magnetic field, a higher plasma current, higher temperatures, which means lots of stored energy in your plasma. And so for the disruptions, this means lots of energy that then has to leave, or lots of energy that can be transferred to runaway electrons. So if we look at this more quantitatively, we can see that this damage could be worse in Spark because Spark has so much stored energy. So the damage that a runaway electron beam can cause is largely related to both the energy of the beam. If you have a very high energy beam, you can melt a lot of material. But it also depends on how large of an area that beam strikes. So if you hit a very small area, you deposit a lot of energy into that area and you're gonna really melt a good section of that. However, if you spread out that energy over a wider area, maybe you won't hit a melt threshold and maybe you'll just cause the area to heat up, but it won't quite hit melting. So this, there is a threshold for which melting occurs, and that threshold is around 3 to 5 megajoules per meter squared for tungsten, which is going to be the first wall material in Spark. And the energy that a runaway electron beam has is proportional to the current squared. And so this is why when we look forward to Spark, which will have a plasma current of 8.7 megaamps, this starts to get quite concerning, because Spark will have the highest plasma current of any device so far. That means that we could see really high energy runaway electron beams, up to tens of megajoules, which is very, very powerful. And so what I've done here is I've scoped what potential runaway electron impacts could look like. So I've scoped from 0 to 8.7 megaamps of runaway electron current. And I've also scoped what the average energy could look like. And then on the graph, I've put the wetted area for which the beam exceeds that melt threshold. So if you look at this simulated Spark case, which was simulated with a code called DREAM, that has about 5 megaamps of current and an average energy of about 8 MeV. And you can see that this lies on the 10 meters squared contour. So that means that this simulated case could melt 10 meters squared of wall area, which is a very large section of wall. So we gotta hope that that does not happen, because that would be quite bad for Spark operations. So what are we gonna do about this is the question. Spark will have some mitigation techniques to mitigate runaway electron beams and mitigate damage. So one thing is massive gas injection. So if you inject some massive gas into your plasma radiates away its energy, and this means that the energy of your plasma gets more uniformly radiated into the walls, rather than a runaway electron beam, which can hit a very small area and deposit a lot of energy onto a smaller area. So the goal is to spread out where the energy goes onto your walls. The other thing that will happen, that Spark will have, is a runaway electron mitigation coil, which is this image that I've put here. And so what this does is it sort of has a funky shape. And when you have a disruption with the runaway electron beam, what the runaway electron mitigation coil does is it introduces perturbations to your magnetic field. It messes with your nice ordered magnetic field, making it a bit chaotic. And so this means that your runaway electrons are just deconfined. So they just exit before they have the chance to cause a very large coherent beam of runaway electrons that can then cause damage. And so we have some mitigation techniques, but what else we are doing is modeling. So that's where I come in. So the goal of my modeling is to determine how bad different runaway electron scenarios will be, and then to determine how we can avoid those scenarios with our mitigation techniques. If we know how bad certain things we can avoid that, and we can make sure that our machine is okay and operates in a safe sense. So, to conclude, tokamaks can get lightning-like beams of electrons during disruptions, and these electrons can damage the walls, which you can see over here in this collage again. And this damage might get worse in future devices, so we need to understand this damage so we can mitigate it better. So hopefully, Spark will not look like this. So, thank you.
Questions from the audience, and if not, we'll take the one from the chat. But first, do any of you have a question?
You mentioned gas injection as a way to mitigate runaway electrons, but that seems to run counterintuitive to the whole tenet of fusion, where you want to try to have as much fusion power as you can in the core. Is there like a trade-off here, and how big is the trade-off?
So the massive gas injection is a thing that you do when you're already operating, when you're already operating in a space that is going towards a disruption, you do the massive gas injection to mitigate the effects of the disruption. So you wouldn't want to have a nicely performing plasma that then you put a lot of massive gas into, because then you just radiate away your power. So it's when your plasma is performing badly, that's when you throw in the massive gas to get it to get rid of its energy in the safest way it can.
Any other questions from in the room? No, we have a question here, which is asking, the RE beams are expressed using energy terms versus using power terms. Is this because the damage is better thought of as an impact, like an instantaneous projectile, versus energy deposited over time?
Yeah, this is a really good question. So the time scale of runaway electron impacts tends to be quite small, I think on the order of milliseconds to sometimes can be even shorter than that. And so that's why we think of it in terms of energy rather than power, because it's basically, you can kind of think of it like an instantaneous thing when the beam hits the wall.
All right. Well, maybe for the sake of time, we'll move on to the next speaker, but let's thank Abby again. We'll take about 30 seconds to transition as we do. Stand here.
Tried running.
Let's take it.
The link is also in one of the emails.
Actually, can you?
I didn't see it.
Henry, no, you're fine.
It's super cool.
Doing it, Henry.
I did, but like,
Henry,
It's just like,
did you join the Zoom room?
I should be in the Zoom room.
Okay, just making sure for later. All right, and Joseph is going to be talking to us in a second about superconducting diodes for quantum computing. And we are just getting this. You got that working?
So,
Okay.
hello. So I'm Joseph. I'm going to be talking about a slightly different topic, actually from plasmas and so on, very high energy physics. I just saw an axis with megaamps. I'm going to be talking about milliamps. So the idea is that we work with superconductors that are very useful materials, as you're going to see, especially at very low temperatures. So let me just get started and motivate why we are doing what we are doing. So you know that there is recently this very large evolution in quantum computers, which are working at low temperatures. And you look at some of the latest, nowadays I think they're already by 100 or 200, but you look at those quantum computers which have like 50 qubits, and then they have a lot of cables around and so on. You compare this with our usual desktop computers, and you see that there are almost no cables laying around. Everything is actually integrated into circuits and so on. And that happens because these quantum computers, they need to operate at very small temperatures, and it's actually hard to have the logic that we are used to operate at room temperature at such low temperatures, because it's very difficult to cool down down to those very low temperatures. You can have milliwatts of cooling power at those temperatures, so you have to be very economical with how you spend energy there. Now, there are some computing approaches which are actually able to do these operations at 4.2 Kelvin, but those actually need some DC power delivery, which in practice implies that you need to have tons of cables going down, and that's why you see all this stuff. Our goal is to find a way to do this AC to DC conversion at these low temperatures, so that all these cables can be removed or just very heavily reduced so that scaling can go farther. That is how we want to do it. And of course, what we want to do there is to do that with what we call superconducting diodes, which are a variant of semiconducting diode, just as a reminder. So semiconducting diode is a system, which is a semiconductor actually, as the name says, which has a very asymmetric response to an applied voltage. So when you apply a voltage between its terminals, if it's in the forward direction, you can get very high current. In the reverse direction, you get a very small current. That means that the resistance in this direction is very high and this direction is very low. Now, this is very useful because it allows for conversion of AC currents into DC, but you see also that this is a resistive system. That means, yeah.
The slides are not changing on Zoom.
Oh, really? Thank you for letting me know. that down. I think share. Okay. Now is it now working? Let's try. Is it changing on Zoom?
Yeah, we're seeing the speaker view.
Ah, shit. Okay. Sorry. Hide speaker view. Where was that? Presenter view. Amazing. Now it should work. Is it now working? Thank you so much for letting me know. Sorry for that. So coming from the semiconducting diode, you have this non-reciprocity of the response. So you have this very large asymmetry between positive and negative voltage, which allows for converting AC currents into DC. But the problem is that it is resistive, so it dissipates heat. So we need to look for an alternative that can work at low temperatures, and that is what we call a superconducting diode. As some of you know, superconductors are materials that can carry current without a resistance. That means that you do not have heat dissipation in that regime. But you know everything has a limit, and superconductors have a limit which is called critical current, and that is how much current they can carry without heat dissipation. Now, if we make that critical current to be direction dependent, meaning that for positive critical current, when you apply a positive current, you need a lot of current to drive the system resistive, and when you apply a negative current, you need much less current. What is going to happen is that you also have this kind of non-reciprocal response, which is very asymmetric between positive and negative voltage. And now that may allow also for the AC to DC power conversion at low temperatures, but then you have a lot of less power dissipation because in this whole regime, you're not dissipating heat. And our goal is to actually make use of these systems. However, first let me just briefly explain you how we make these superconducting diodes. What we do is we actually make use of what is called the Meissner effect, which is this property of superconductors that they repel magnetic fields. The idea is that you apply a magnetic field to a superconductor and it's going to repel it by creating what is called a Meissner current inside. So here you have a circulating current that is going to oppose the flow of this magnetic field inside. Now, if we make a device which is just an ultra-thin stripe of a superconductor, we apply a magnetic field perpendicular to the plane. That means that at the opposite edges we're going to have opposite Meissner currents, as you can see here. Now, since this is just the top view of the sample, when you apply a positive current, meaning that it's going up, as this purple arrow shows, we have that at this edge we're having a very high current, but at this other edge we're having much smaller current. If we reverse the current direction, then what happens is that this edge is the one that has more current. Now, we are using a type of superconductors which are called type 2, where the edges are actually the ones which limit the critical current. And that actually means that because we have made these notches here, we have reduced the critical current of this edge, and now by controlling the direction of the current, we can have a low critical current in this direction and a high critical current in this other direction. However, this technique requires a magnetic field to be applied on the sample, and we want to get rid of that. So what we do is the following. We just place a ferromagnet on top of the superconductor, and now we have the stray fields from the ferromagnet which have opposite sign in both edges, but they actually result in having a Meissner current that has the same sign of both edges, because the very edge is what limits the critical current. This allows you to have a diode even at zero magnetic field. That is useful because it will not disturb other superconducting components working next to it. Now comes the part of converting AC currents into DC. I mean, we have all gone to high school and we have all seen what a diode bridge is. So the question is, how would that work when instead of having semiconducting diodes, we actually have superconducting diodes? Now, the rules of the game with superconducting diodes, as I told you, is that the resistance is zero when the applied current is very small. But then if the applied current is either higher positive than the critical current in forward direction or lower in negative than the applied current than the critical current in the reverse direction, then it's going to turn resistive. Now, we can see just simply what is going to happen to this circuit. Here, the moment we apply a positive current, you can see here that half of the diodes will become resistive, and it's going to be the ones where the current is opposing the arrow, as defined here. And what you see now is that you apply a positive voltage here, and eventually you get a positive voltage here. Now, the moment that we reverse the applied current, again, this is reversing the diodes which become resistive because it's the ones which are opposing, and so you end up having again, a positive voltage on this side. And this is how the full wave superconducting diode rectifier works. Now let me just show you a little bit on how our results look like. So we made the superconducting diodes following these techniques that I told you. And then we just applied some AC currents as an input. And then you see how the output shows this full wave rectifier operation. And then, of course, we apply a magnetic field, which is reversing our diodes, and we can just have a programmable rectifier in a sense. You're not fixed by the device design, but you can use magnetic fields to tune it. So you can reverse the diodes. You can get opposite signals. And then finally, we just replace the resistor with a smoothing capacitor. And now you have AC to DC conversion, as people do conventionally at room temperature, but now we have done this one at 1.8 Kelvin. And that is the goal that we had here. So sorry, it's 1.7 Kelvin. To be precise. And with that, I hope I have convinced you that by exploiting Meissner currents, you can create what is called superconducting diodes, which are these non-reciprocal superconductors that are useful to, for instance, make full wave rectifiers working at low temperatures that are capable of converting AC currents into DC, and that this is actually useful for superconducting quantum computing. And with that, I thank the collaborators and you all for your attention.
A little behind, but we can take one question if there is a question.
So you mentioned that this uses type 2 superconductors. Do you think that, with all the excitement around high temperature superconductors, does that also have applications for, power electronics for quantum computers?
It could, but so it's it needs to be type 2 to work with this method, but any type 2 will work. Indeed, high TC usually they tend to be type 2, right? Yeah, it's usually a matter of the condition at which you need it to operate. The main thing here maybe is that you don't want to operate at 77 Kelvin because typically wirings and everything that connects down, these are resistive wirings, but usually below 4.2 Kelvin people use niobium and so on. So you can have superconducting interconnects between the different levels. So if you may use a high TC superconductor, but you eventually want to use it either at 4.2 Kelvin or below. So the benefit will not be so much unless you want very high critical current for specific high power application.
I see.
Let's thank Joseph again. Next room, Xander. Oh yeah, thank you. What do you need?
Got it. Can the people on the Zoom see this?
Is it? Great, thumbs up. Right. Xander is going to be talking to us about disruption prediction with scientific machine learning.
All right. So. For the last 60 years, tokamaks have dominated magnetic confinement fusion research. So this is because tokamaks have excellent particle confinement and there we go. Excellent particle confinement and have demonstrated 100 times better performance than other magnetic confinement fusion designs. Further, their simple donut-shaped geometry make them relatively easy to build. As such, there have been dozens of tokamaks constructed around the world, and the research community has decades of experience operating them. Given this successful experimental history, we think tokamaks are the natural choice for building a fusion pilot plant. However, tokamaks have a little bit of a problem. in that they are prone to instabilities, and these instabilities can lead to disruption, as Abby was mentioning earlier. So disruptions are kind of a problem. Now, when I say that the nuclear fusion power plant can experience a sudden loss of confinement, you might picture something like this. Fortunately, that can't happen, and this is one of the few parts of the fusion propaganda which is actually true. So tokamak disruptions actually look like this. So there's zero risk of a runaway chain reaction leading to a Chernobyl-style accident, because if anything goes wrong, the plasma rapidly expands and cools and the reactions stop. So one instant your plasma is there, and the next it is gone. Now, while disruptions pose zero risk to anyone outside the tokamak, they are still a concern for the device itself. So future tokamaks like Spark will have hundreds of megajoules of stored thermal energy and mega amps of plasma current. So when confinement is lost, all this energy and current have to leave the plasma, and it goes into the surrounding structural materials extremely fast, causing large heat flux and halo current forces. To put these numbers in perspective, the heat shield of an Apollo capsule during re-entry experiences a peak heat flux of only 1 gigawatt per meter squared. And a Saturn V rocket first stage has 35 meganewtons of thrust. So we want to avoid disruptions in Spark because they pose significant materials challenges. So preventing disruptions means you need to avoid instabilities, so you want some dynamics model so you can predict how the plasma will evolve in the future. As I said before, tokamaks have existed for over 60 years at this point. We must have comprehensive methods of determining exactly how plasmas will behave in a variety of circumstances, right? Well, yes and no. There are some models that have proven to be extremely valuable, such as ideal MHD, but there are others that continue to present challenges. These are things like turbulence, plasma material interaction, magnetic reconnection, etc. In addition, any solution that you develop must be compatible with real-time operation. As it stands, disruptions are a problem that cannot be solved with theory alone. So we must look for an alternative. In 1687, Sir Isaac Newton said F equals ma. Newsflash, it's 2025. Sir Isaac Newton is dead. It is time for a new paradigm. F equals ma plus AI. Let me give you an example. Say we wanted to have a predictor for the plasma beta. Beta is simply a ratio between the between the plasma pressure and the magnetic pressure. The beta limit is an important consideration for keeping the plasma stable, since if the plasma pressure is too high, you can't confine it with a magnetic field and instabilities will rapidly form. Beta can also be written in terms of plasma energy versus magnetic field energy. So to predict the value of beta over time and ensure we don't exceed the beta limit, we just need to predict energy in the plasma over time. Good so far? All right, cool. We can write out a simple equation for the change in stored energy over time according to various power sources and sinks. As sources, we have things like ohmic power and auxiliary heating. As sinks, we have radiant power and conductive power. Most of these terms we can measure decently well in real time. The conductive power is tricky though, because it depends on energy confinement time, or how long it takes energy to leave the plasma. That means it depends on turbulence, micro instabilities, pedestal physics, blah, 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 whatever. This is really annoying to work with. And even our best codes cannot really estimate it well in real time. So let's ignore all that and replace this term with a neural network. So here's our new equation. All we have done is replaced the energy confinement time term with the output of some data-driven model. And when we train the network, the loss function will be in terms of plasma energy. So it's not machine learning, it's scientific machine learning. Setting up the problem in this way has several very real advantages over traditional machine learning, which would attempt to predict plasma energy directly. First off, it's interpretable. We're following the structure of this equation. I can easily see how the output changes based on the inputs. And again, we can measure most of these inputs. Second, it makes training easier. Like A fully black box approach would require a larger model, which would need more data, and that's difficult to come by when we're first commissioning new tokamaks. Another thing that this does is it mitigates overfitting. So because we're restricting the influence of the model to just this one component, it means that our results are more likely to be, physically meaningful in some sense. So here's an example of the model in action. This instance in particular is a full shot rollout. So we initialize the stored energy at the measured value at the start, and then extrapolate for the entire shot. And as you can see, it works rather well for predicting the plasma's energy. Also, I chose this example because it highlights what the model is trying to do and what it is not trying to do. The output of the model may be the predicted energy confinement time, but it's not trained to get an accurate energy confinement time because even our best simulation codes have difficulty determining what that should be. Rather, we're staying in the realm of well understood physics. In this case, it's just power balance. But we aim to extend this to other parts of tokamak operation, such as magnetic control, which operates with ideal MHD, which is an area that has proven to be at least decently robust during routine tokamak operation. So, in conclusion, instabilities that lead to disruption are a major concern for the operation of future tokamaks. Preventing disruptions will require the ability to forecast if and when the instabilities appear so they can be avoided. Predicting complex plasma dynamics from theory alone is extremely challenging. But scientific machine learning is a promising path forward, allowing us to combine physics with data-driven methods to improve our modeling capabilities. Thank you.
Any questions for Xander?
Thank you for the talk. I was wondering whether you can reverse the problem. So from the machine learning that you're doing, can you learn back the physics of the system from reading the?
Yeah, sure. I mean, you can kind of see here that's essentially what's happening, at least in this regime, right? Like the model doesn't know what the correct energy confinement time should be, but you see that by predicting the evolution of stored energy, you kind of back it out here. Yeah. I mean, like this calculated measurement is from a code running in post-processing from this particular shot. So it's like your the best estimate from codes, like what it really should be. But again, you can see there's disagreement, even though the model, it's accurately predicting the energy confinement. It's predicting the stored energy, but there's disagreement in the confinement time. So something somewhere isn't adding up. So which do you trust more, I suppose?
I was just wondering, after you run your model and you get your feature importance out after it, is there anything that disproportionately, like any inputs that disproportionately affect sort of what's going on in predicting your stored plasma energy, or are you saying sort of all inputs are weighted equally with the feature importance after for when you get your predicted plasma?
It isn't so much that we're doing feature importance, like we're just picking one term which there isn't really a good model for, there isn't a good first principles model for, and replacing that with data-driven methods.
Let's thank Xander again for the sake of time. And have our last speaker, Henry, come up. Able to see it? All right, Henry's going to talk to us about UFO disruptions in tokamaks.
Cool, so I'm Henry. I'm a graduate student at the Plasma Science and Fusion Center here, and today I will be talking about UFO disruptions in tokamaks, which sounds very mysterious.
Screen split or the Zoom?
You're showing the speaker view.
Oh.
Oh, yeah.
It's right on Zoom.
You want to share screen or?
Oh, yeah.
Back into presenter.
If you share your screen, rather than sharing window of PowerPoint,
Oh, yeah.
share desktop one.
That's what we had at first.
Yeah, that worked for me. So. Yeah, now it looks good.
That looks good. Okay, cool. Thanks, Sean. So as others mentioned earlier, so tokamak is this toroidal plasma where we have this strong toroidal magnetic field produced by external magnets, and then we drive a current in the plasma, which produces this weaker colloidal magnetic field. And so, as you may have learned in like an introductory physics class, a charged particle will approximately follow field lines in this helical trajectory around a magnetic field. And it roughly holds for tokamaks. And so particles can travel quickly in the toroidal or colloidal direction along these field lines, but any particle transport out radial, perpendicular to the field lines towards the wall, is restricted. So that's the principle of magnetic confinement. And as Abby and Xander mentioned, we want to do fusion, we want to hold this tokamak plasma in equilibrium for at least a few seconds, hopefully longer. So that means you need our plasma to be stable. So a common analogy for stability is picturing like a ball at the bottom, at the valley or peak of a hill. So in a stable equilibrium, that's like a ball at the valley of a hill. Give the ball or plasma, in terms of fusion, a little kick, and it'll return to its original state. But in an unstable equilibrium, that's like a ball at a peak of a hill, give it a little kick, and it'll move far away from equilibrium. And that leads to, as Abby and Xander mentioned, disruptions. So there's plasma goes unstable, and we have a sudden loss of thermal energy and current. And as both Xander and Abby talked about, that poses severe risks to machines, especially as we build larger devices with higher thermal energies and currents to do fusion. And as Xander talked about, from a controls perspective, if we notice the plasma going from this nice stable regime to some unstable regime, we need to take a control action. Either that could be we have enough time returning our plasma to a stable regime, or at least mitigating the damage of a disruption. So one type of disruptions in tokamaks are called UFO disruptions. So in fusion, UFOs don't have anything to do with flying saucers. Instead, they mean a flake of a metal impurity, usually like from the wall, like tungsten or molybdenum, as others talked about, that could flake off and fly into the plasma, and that'll radiate a lot of power. And so much so that it could radiate a significant fraction of the plasma thermal energy away and lead to a disruption. So if you're operating a machine, you might see some like glowing speck of metal fly in and enter this kind of transparent plasma, and you'll just see it pop like a balloon, as Xander showed. And so here you can see on a picture of CMOD, potential origin, suspected origin of a UFO disruption, where you can see that a piece of the wall got misaligned. You can see there's this leading edge in the yellow box which experienced an unusually high heat flux since that piece of wall was exposed. And you can see there's some melting, probably some liquid molybdenum droplets entered the plasma and quickly caused a disruption. So what does this look like if you're operating a machine? So here's an example of a time trace from an experiment on Alcator CMOD, our old tokamak at MIT. So in the top panel, we have the plasma current. That's nice and steady, around 1 mega amp. And we're about like 1.2 seconds into the plasma pulse. So in CMOD, a typical plasma pulse would be 2 seconds. The second panel is the molybdenum content in the core of the plasma, so that's nice and steady, which is good. We want that to be low. We don't want any wall material into our plasma. The radiated power is steady, which is nice. And then this bottom panel is the electron temperature of the core of the plasma, which has this kind of funky sawtoothing shape, which is the sign of a healthy plasma in the tokamak. But then you can see in this red box, there's a sudden spike in the molybdenum content in the core. The radiated power rapidly increases to about 8 megawatts, and that's totally exceeds the heating power. So we see a quick thermal quench and quench of this current. And what's particularly concerning about this is if you look at the time scale of this event, the time we have from the, any noticeable sign of the injection in this panel to the disruption is about 5 milliseconds. So that is too short to take any control action. So on Spark, we'll need at least something like 10 milliseconds of warning time to at least mitigate the damage of a disruption. We want to avoid the disruption. We need longer warning time. And so this poses a serious problem because in like a power plant, if you have all of these UFO disruptions like we had on CMOD, that could really damage the machine, and that's not compatible with the economics of a power plant. The good news, though, is that not all UFOs on CMOD cause disruption. So here's another example of a molybdenum injection on CMOD from a piece of the wall, and this did not cause a disruption. So we have the same 4 signals here. You can see a sudden spike in the radiated power and molybdenum content. And the radiated power here only slightly exceeded the heating power, which isn't shown. So you can see the core temperature decreased, but the plasma did not disrupt. It also decreased over a longer time scale. And so this is okay. And it also gives us a picture of maybe what a stability of a CMOD plasma might look like to these UFOs or radiative events. So maybe a small injection, like in this one, is like the ball in a valley. Give it a small kick, it's stable. But if you give it a large enough injection, like I showed previously, and the plasma will move to some totally different state and lead to a disruption. So what might set these stability limits? This is something we want to figure out to these radiative events. Basically, what sets the height of these peaks versus the depth of the valley? So that could be things like the external heating power we're supplying to the plasma. It could be like the stored thermal energy of the plasma. Higher stored thermal energies will take longer to radiate the energy away. It could be also proximity to like fluid instabilities, which can depend on like the current profile. And it could also just be the operational history of the device, like how damaged are the walls from either previous disruptions or just accumulated damage, as others have talked about earlier, that can happen to these walls. So that's kind of led to the project I'm working on. So we'd like to find some parameter space, both with plasma parameters, operational parameters, where in which plasmas are more robust to these UFO disruptions. So maybe it takes a longer time for the plasma to disrupt, where there would be ample time to mitigate the damage, or maybe where plasmas would just not disrupt and be able to recover. So we're labeling UFOs on thousands of discharges from Alcator CMOD. For each UFO, extracting relevant plasma parameters and operational parameters. Maybe doing some fancy machine learning to identify any correlations, and then we'd like to compare to UFOs on other tokamaks. So we recently started a collaboration with West, a tokamak in France, that on a recent campaign experienced lots of similar UFO disruptions.
Just about to say we've got about a minute left.
Okay, yeah, so thank you.
Great to
And
have questions.
any
Yeah,
questions?
Time for a question or two, and then we should call it.
So these UFO-based disruptions, they're basically like a thermal quench of the plasma, is that right?
Mm-hmm, yeah.
So you wouldn't need to worry about like runaway electron generation or anything from a UFO being tossed in.
Well, so what can happen is, so like one question is maybe, how severe is the damage to a UFO? Because it is something that like radiates energy away, and that radiation is uniform. I don't know if like that's kind of what you're.
Yeah, like what is the damage to the machine from these UFOs besides just like you lose your plasma?
Yeah, so often what will happen is it might not radiate quite all of the plasma thermal energy away, so it won't radiate as much as like if you do some like massive gas injection or like shattered pellet injection, like machines use to mitigate the damage. So it might radiate like half the stored thermal energy, but since that radiation is localized where the UFO is, that might change the like temperature and therefore current profiles, which can lead to some MHD instability, like some kink mode or tearing mode, and that can then cause a more typical disruption where you have the heat fluxes, high heat fluxes on like on the diverter, and yeah, these like current halo current stuff like that.
Thanks.
Any other quick questions? If not, we have gone close to overtime, so let's thank Henry again. Thanks to all of you again. This was amazing and a lot of fun for me. And I will now end the Zoom recording so you guys can live your lives.